Hello everyone, I am Diana David from Steel Founders Society of America. Today I'll be presenting about Digital Innovative Design for Reliable Casting Performance or our DID program. I want to start with a question for you to ponder on for a few seconds. Why do you think did the Titanic fail? Was it caused by an inclusion in the steel? Was it caused by porosity? Answer to both is no. The Titanic failed because it hit an iceberg. There's always the perception that parts fail because of a defect. When castings fail, metallurgical analyses of the part would usually attribute the failure to an inclusion or a porosity. Failures are not caused by defects. It is caused when the part is loaded beyond its capacity. Any part, even if it's defect free, regardless of its product form, whether it's a casting or a forging or a rolled plate, it will fail if the load exceeds the design limits. So steel is steel, no matter what the manufacturing process is, no matter what the product form is, whether it's a casting or forging, they're all melted the same way. They start with the same raw material and they're melted in a furnace. Steel castings have a wide range of applications and they can be used in high stress applications. The load bearing capacity of a casting depends on the geometry, material properties, and quality. Selecting these requirements is the responsibility of the design engineer. Unfortunately, designers lack the tools to know the performance or set quality requirements for steel castings. It was thought that designers are wimps. They don't know what they're doing and what they want. But years of experience on dealing with castings have made them knowledgeable about the design and the casting process. However, we face the challenge of losing that experience and knowledge once those design engineers retire, and the stream of younger engineers that may not have been exposed to castings yet inherit the design responsibility. Another challenge that we faced is cast alloy grades are called out differently from their wrought counterparts. For example, the buyer wants a 17.4 pH stainless steel. The foundry calls it out as CB7CU-1, different designation but the same alloy. Another thing is when you buy a wrought alloy, say a 4330 plate, there is no NDT called out. You buy a plate and you know what you're getting. In the building construction industry, they buy a part from the shelf, they weld it to another part, and they know the fatigue life cycle they will get for that fabrication. Casting design and specification can be overwhelming to a designer unfamiliar with the design space and who may not have access to a colleague with decades of experience with castings. The Digital Innovative Design for Reliable Casting Performance or DID program aims to address all these challenges and hopefully bridge that gap between designers and foundries. We have two design objectives. First is to develop a code-based design allowables, much like ASME boiler and pressure vessel code, where it specifies allowed stress for specific grades. The second approach is developing a model-based process and performance design. We will leverage our modeling capability in establishing lower bounds for local properties in steel castings. To accomplish both design objectives, we need to develop quantitative NDT methods to be able to correlate casting quality to performance. We are very fortunate to have a team of experts from the industry, the academia, and Department of Defense. Our whole team is collaborating to achieve our program objectives. Our first design approach is establishing code-based design allowables with embedded NDT. This is a conservative design method where properties assumed uniform in the entire part, so a safety factor is incorporated to the design. Design limits are specified using codes and standards such as the ASME boiler and pressure vessel code. The design flow chart for boiler and pressure vessel code components is shown on the right. So the rules for construction of specific components are in sections like Section 1 for power boilers and Section 8 for pressure vessels. They then call out Section 2 for material properties. Let's use a common carbon steel grade as an example, ASTM A216WCB, which has a minimum yield strength of 36 KSI. Per Section 2, the allowable design stress is 20 KSI. Based on the quality factors set by the section for that specific component, if NDT will be done, then you can use the full allowable design stress, which is 20 KSI. If no NDT will be done, then the code only allows you to use zero point 0.8 of the design allowable stress, which was 20 KSI. So the allowed design stress without NDT is only 16 KSI. If NDT will be done, Section 5 is called out, and for any components that need to be welded, Section 9 is called out. These boiler and pressure vessel codes lay out all the requirements for material, allowable design stress, NDT, and welding that designers can specify for the components they need. Our DID program aims to develop an approach similar to this by establishing design allowable for cast steels with embedded NDT requirements. Steel castings and structural applications offered a great case study for us. Cast steel components have not been used in building construction because builders, engineers, and architects do not know the cast steel grades, design practices, inspection requirements, or welding procedures. We aim to bridge this disconnect by demonstrating the weldability of cast connectors and providing more guidance to designers and fabricators. AWS D1.1, which is the welding standard for structural steel, have pre-qualified base metal. So this allows the use of D1.1 pre-qualified WPS, meaning you don't need to do any qualification testing of your weld procedure as long as you use a pre-qualified base metal and stay within the pre-qualified welding parameters specified in D1.1. Cast steel grades are currently not pre-qualified in D1.1. We are working on a proposal to add a carbon steel grade and a low alloy grade to the code. To demonstrate that cast steels are weldable like the wrought grades of similar chemistry and that castings can be fabrication welded to other building construction components, we conducted weld trials and performed all testing that can be done. This table summarizes the tests required for the plate thickness we use per D1.1 and other welding standards, and all the other additional tests that we did. We welded cast WCB to cast WCB, and we welded cast WCB to a wrought grade A516 grade 70. And to provide the baseline, we also welded wrought to wrought, so A516 grade 70 welded to itself. The same filler material was used in all the weld plates. The test results were all acceptable, although we did retest some of the bend bars, but per the standard we were able to retest. We did 2 retests for each failed bend bar. I want to make a point that I'm not trying to show that the cast WCB has higher properties than the wrought grade tested. I'm just showing that cast grades are also weldable like the wrought steel of similar chemistry. The microstructure of the samples were examined, and this micrograph shows the weld cross-section. It was etched with 2% nitrile to reveal the fusion zone microstructure and the weld quality. There were no welding defects observed, so we measured the microhardness across the fusion zone to identify if there are any unexpected hardness variation. The left side is cast WCB and the right side is the wrought A516 grade 70, and then the center is the weld. Higher hardness in the heat-affected zone was observed on both sides. Here are some DIC pictures for A516 welded to itself. DIC is digital image correlation. These DIC images show the strain in the tensile specimen during tensile testing. The fusion zone marked as FZ in these images is in the gauge area. Pink and purple is low strain and red is high strain. The leftmost image is a tensile specimen at the beginning of the test, and moving from left to right shows the specimen as the test progresses. You could see that the strain builds up in the base metal and fracture eventually happens in the base metal. This does not say that A516 has low properties, because if you pull a specimen, it has to fail somewhere. It just so happened that it failed in the base metal, which is actually where we want it to fail because this shows that the weld performed well. These are now the DIC images for the WCB welded to WCB. The strain localization is similar to what we saw in the last slide for the A516 grade. Fracture occurred in the base metal. Same as what we saw in the A516 specimen, the weld for this cast grade also performed well. To further demonstrate that steel castings can be fabricated welded to other building construction components, we are welding actual castings to HSS, or hollow structural steel. Similar to what we did in the weld plate qualification testing, we are staying within the pre-qualified welding parameters specified in D1.1. We'll do full-scale testing, and we'll also section test coupons to do tensile test, bend test, Sharpie V-notch, and microstructural analyses. So this just shows the castings to be welded and their dimensions. So we're welding both ends of the casting to HSS, and we're testing several weld joint details, and we're going to test as cast versus machine surfaces. Our end goal is to develop a design guide for steel castings that the building construction community can use. Providing a design guide like this would make the use of steel castings as structural components more straightforward and less cumbersome. Now to our second design objective, which is the model-based process and performance design. We collected thousands of heat data for common cast steel grades from our member foundries. Using the MMPDS approach, we analyzed the heat data and established A and B design allowables. The A design allowable is the first percentile of the normal distribution of 95% confidence interval, meaning 99% of the data is higher than this point. B design allowable is the 10th percentile, or the value where 90% of the data is higher than that point. The plot on the left illustrates these points. The plot in the center shows the normal distribution of the yield strength for our quenched and tempered 8630 dataset. The average yield strength for this dataset is around 109 ksi with a standard deviation of about 14 ksi. Looking at the probability plot on the right side, there are some data points that are beyond the plus minus 3 sigma or 3 times the standard deviation. These encircled data points are considered as outliers. These plots show the A and B design allowables for the other 8600 grades. The plot on the left shows the yield strength, while the plot on the right shows the ultimate tensile strength. The red bars are the 1% lower bound or the A allowable, and the blue bars are 10% lower bound or the B allowable. There are some slight differences in strength values between normalized and tempered versus quenched and tempered. As expected, the increase in percent carbon brought up the strength values. Lower bound property analyses that I showed in the previous slides were on heat data. For each steel heat that foundries make, they test the quality of that heat by testing specimens from a test coupon, usually a keel block. The picture on the left shows a standard keel block. It typically has 4 legs or 2 legs. These legs are machined to a tensile bar or Sharpie V-notch bar. The test results of these keel block specimens should meet the material specification requirements to qualify the heat. The test results are not intended to define the upper and lower limits of tensile properties within a part poured from that heat. This is true for all product forms, whether it's a casting or a forging or a plate. All ASTM material specifications acknowledge this. Properties vary within a part. Under our DID program, we are investigating this lower bound property in steel castings by considering different quality factors such as section thickness, heat treatment, welding, and surface conditions. We are sectioning actual castings to determine the range of mechanical properties that can be achieved. We are leveraging the advanced modeling capability to investigate various modeling parameter indicators such as porosity, solidification rate, cooling rate, thermal gradient, Niyama criterion, to name a few. So this slide just shows some examples of castings that we are cutting up and taking specimens from. Here's another example of test coupon that we cut up and took tensile specimens from. This is a 4-inch Y block which is used to qualify thicker castings. The picture on the top right shows the tensile specimens that we sectioned from this Y block. Using casting simulation software, we calculated solidification parameters for these tensile specimens, and the plots on the bottom right shows the predicted phase fraction of bainite and martensite for these specimens. Using the modeling results, modeling parameters were correlated to measured tensile properties to establish prediction curves that move us towards the capability to predict the lower bound properties. Currently, casting simulation software can predict strength properties, but it is not accurate. In this preliminary analysis of this specific dataset, thermal gradient seems to correct the over-prediction of the software. Further analysis is needed to establish this relationship and to identify what other parameters can more accurately predict properties. To push us towards a more quantitative NDT, we need to have test data for steel castings with indications. We will develop a methodology that would allow designers to assess if the steel grade would behave in a ductile manner or a brittle manner. We are using fracture mechanics to look into the relationship between NDT indications and performance. Fracture mechanics approach using K1C value allows evaluation of how a material with a certain indication size would behave under an applied load. K1C is fracture toughness, or the value that represents the material's resistance against crack propagation. So if you plot K1C versus yield strength in English units, you can draw a line for K1C to yield strength ratio equal to 1. This splits ductile materials versus non-ductile. The grades above the line are ductile and the grades below the line are non-ductile. These non-ductile grades are more sensitive to indications or even small indications would matter. For example, in fracture mechanics, you can determine the critical flaw size based on K1C and strength. For a carbon steel grade like WCC, the critical flaw size is 3¼ inches. For 4340, which is a much higher yield strength and lower toughness than carbon steels, the critical flaw size is only 0.2 inches. To test actual specimens with indications, we designed and made cast plates that have some gross surface and subsurface indications. These levels of indications are much worse than what can be found in typical castings. The castings were inspected visually and radiography tested so we could identify where the indications are and where we should take tensile specimens from. In addition to the surface and subsurface indications that we designed to be in the casting, we also manufactured indications by drilling holes in the specimens. Sound tensile specimens were also tested as the baseline. These are two tensile specimens with indications that we tested. The leftmost one failed along where the indication was, marked by the red arrow. Interestingly, for the second tensile specimen, it did not fail where the indication was, again marked by the arrow. It failed near the bottom grip. Apparently, there was a shift in the pattern when the casting was poured, which caused that thickness to be smaller than intended. The indication did not reduce the cross section enough to make it smaller than the area where it actually failed. The ductility dropped as the indications become larger in the tensile specimens that we tested. However, measured tensile strength did not show a clear trend with indications. But even with indications, the castings could still handle the load, which brings me back to my first point, which is steel is steel. FEA was done, and these modeling results are being used to develop a ductile fracture index to relate the presence of indications to the performance of the steel. This ductile fracture index seems to have a potential as design parameter for steel castings. In addition to correlating modeling results to mechanical properties, we are characterizing the microstructure and other features on tested specimens and correlating them with properties. One measurement that UAB developed when we were working on a cast high-strength low-alloy steel a few years ago was this max pore cluster size. Using a stereo microscope, microporosity on the fracture surface are marked as shown in this image. Indications are measured as a cluster instead of individually. If the distance between adjacent pores is less than the largest adjacent pore, that's considered the cluster. Only the maximum or the largest cluster size is measured. Fracture surface analysis is a good technique to confirm any unusual features in the specimen. However, it cannot be directly compared to predicted porosity from modeling because the predicted porosity is across a planar surface. Other measurements that we do is quantify the fineness of the microstructure by measuring grain size or dendrite arm spacing, although they're not always an easy measurement to do. The faster the cooling rate, the smaller the dendrite arm spacing tends to be, so these measurements can indirectly demonstrate effective cooling rate which can be predicted by the modeling. Here is an example of an L-shaped casting that we sectioned and took tensile specimens from. We measured max pore cluster and dendrite arm spacing, and the plot shows that percent elongation decreases with increasing max pore cluster. Besides tensile properties, we are also investigating fatigue performance of steel castings. Fatigue is controlled by the largest feature. It was hypothesized that the surface roughness of castings does not control its fatigue performance because it is not the largest feature. We cast plates with different levels of surface roughness based on strata surface comparator plates. The plates were designed so we could extract tensile specimen with at least two as-cast surfaces. So these cast plates were made with much more severe indications that are actually in production steel castings. So this shows our preliminary results for WCB specimens that were fatigue tested. X-axis shows the different strata levels. A0 is the smoothest surface and A4 is rough surface. Results today show that surface roughness does not seem significant to fatigue life. All samples achieve at least 200,000 cycles, some even almost a million cycles. So this also shows that unless you're dealing with really high cycle fatigue applications, castings even with a gross indication can perform well. For us to correlate modeling, microstructure, and NDT to properties and performance, we need to develop quantitative NDT. Current NDT standards are workmanship standards. They are subjective. Although they do give assurance that at a minimum the castings are sound, there is no correlation established between NDT levels and performance. I'd like to make a point that NDT process is the same for all products, whether it's a casting or a forging or a plate. We all face this issue of repeatability and reproducibility. This shows previous gauge R&R studies in visual inspection and RT, which show that these methods are subjective. Under the DID program, we are working towards developing quantitative NDT methods, and the early work has been on improving gauge R&R of magnetic particle inspection. We are identifying the sources of measurement error, and we will aim to minimize them. We'll also develop aids to help inspectors in identifying indications. We are also leveraging research projects which are sponsored under different programs. Iowa State is developing a digital surface inspection that aims to output a single surface roughness value from scanned data of the casting surface. UAB is developing a semi-automated image analysis to identify indications in bright digital x-rays. The DID program will enable the casting industry and develop design tools that would allow modern engineers to design castings confidently and elegantly. So in this presentation, I provided an overview of our two proposed design methodology and the research we are pursuing to achieve these. Before I end, I want to acknowledge the Defense Logistics Agency for sponsoring the DID program. That's the end of my presentation. If you have any questions about our DID program or about steel castings in general, feel free to reach out to me. Thank you and have a good day.